Hello, class. Okay, so we're going to talk about capacitors and dielectrics today. So I'll start out with what is a capacitor, and we'll basically show one here. Say we have two conductors, which could be anything, but we call them plates, regardless of what the actual conductors are. And the reason for that is one of the most common conductors is, one of the most common capacitors is called a parallel plate capacitor, where you literally just have two metal plates very close together. And so, whatever the conductors are, we call them plates. And overall, the conductor or the capacitor is electrically neutral. We just have two ordinary metal plates, bring them together. But if we hook up a wire, let's say temporarily, let me erase this and just ignore these red lines for a moment. So let's say we temporarily hook up a conducting wire, so just like a copper wire or something. So now charge can flow, from one plate to the other. So one way we could do this is, what if we just hook up a battery to different terminals of a battery to the different plates? They'll be at different potentials, and charge is going to flow. And then we remove the wire, and say we end up with Q on one plate and minus Q on the other. And so again, it was electrically neutral. We're not introducing any charges from anywhere else. So we're just moving charges from one to the other. And so they have the same magnitude of charge, just opposite side. Like this one, say Q is a coulomb. This one lost a coulomb. This one gained a coulomb. But overall, we still have zero net charge. And if this one's positively charged, and the electric field might look something like this. Remember, the electric fields are perpendicular to the surface of the conductor. There's some idea of what the electric field would look like. Now, the conductor, or the capacitor, is a pair of conductors. There's really nothing that says it has to be two. You could have, multiple. You could have a third conductor and just say the capacitance of the overall system. But typically, it's, just two. And there's a pair of conductors. We treat this as a single capacitor with a charge Q. So what that means is one of them has plus Q, the other plate has negative Q. And these red lines I drew are the electric field. And we know if there's an electric field, we know there's a, we can write down this equation. So if there's an electric field in the region, there has to be differences in potentials. The potential has to be changing. And we also know that electric fields go from high potential to low potential. So there's a potential difference between these two plates. And this plate here is at a higher potential than this one. So let's set this equal to 0. And the other plate just has a potential of V then. And so, again, it's a pair of objects, but we treat it as like a single thing with a charge Q and a potential V. So it's just important to know what those mean. If it has a charge Q, it doesn't mean the capacitor has an excess of charge. It's just, one is positive, the other is negative. And if we say it has a potential V, that's a potential difference between the two plates. Now the question is, how are Q and V related to each other? And that depends, what could that depend on? Now, one thing you might think about the charge, but it turns out that's actually not the case. So we could have these two, I'll draw it as separate. Let's look at a parallel plate capacitor. So let's say we have two parallel plates, and they are uncharged. So there's no electric field, there's no potential difference, no charge, but this still has a capacitance. The capacitance is just a property of the capacitors themselves. It has nothing to do with how much charge you put on it. So what factors can affect it? Basically, the answer is geometry. Like in this case, for the parallel plate capacitor, the area of the plates can affect the capacitance and the distance separating the plates. And it turns out, for now, those are the only two factors that will affect the capacitance of this parallel plate capacitor. We're going to talk about a third factor later, but for now, we'll just leave it at 2. Okay, now let's see how the charge and the voltage are related to each other. Again, it depends on the actual type of capacitor. But you might think, like, what if we put a charge Q on these plates? There's a certain potential difference between them. What if we double the charge? Well, then the potential is going to double. It's just a direct proportion. So we can say that Q is proportional to V. So maybe a better way of looking at it, say you hook up a battery to the different plates of the capacitor. So you apply a potential difference, and that causes a certain amount of charge to flow from one plate to the other. And so the charge depends on the voltage. And to turn this proportional relation into an equation, we introduce a constant, which we call the capacitance. So C is capacitance. And capacitance is measured in a unit called a farad. So in words, it's, I write it farad with a lowercase f, but the unit is, capital F. Now, this was named after Michael Faraday. So normally you would capitalize it, but units, you're not supposed to do that. So, okay. Michael Faraday was very interesting because he was one of the greatest physicists of all time and had no mathematical training at all. Basically none, anyways. Like I've heard, he would actually struggle in an algebra class. Now, some do say like he was one of the greatest, or a very great mathematician anyways, but it was all just instinctive. Like he had this great insight, but he couldn't put it into symbols because he never learned that. Kind of like I heard, like Jimi Hendrix, one of the greatest guitar players ever, but he never had any formal training. He just practiced and learned how to do it by sound. So I think it's kind of like a similar thing with Faraday. Now we can see from this equation, Q is the charge that's measured in coulombs. Actually, I'm going to write this equation here as well. Because that's a basic equation. We want to leave that on the board. Now, unit conversion factor. So, charge is measured in coulombs. Capacitance is measured in farads. And potential is measured in volts. So, we have a coulomb equals a farad times a volt. And this does get confusing. Definitely confuses me sometimes. Because when you look at this equation, C is capacitance. Over here, it's coulomb, where the capacitor is represented by F. So just keep in mind you're talking about variables here and units here. So, but yeah, that kind of throws me off sometimes. But just think about it, and yeah, as long as you kind of go slowly and carefully, shouldn't be too much of a problem. Okay, so we have this basic. Basically, you can see this as a way of just defining the capacitance of a system like this. We can just define capacitance as the charge over the voltage. So if we apply a certain voltage to a particular set of conductors, we'll get a certain amount of charge. If we just divide those, we define that to be the capacitance. And basically this is saying that there's a linear relation between them. Okay. So now we want to know, like, how would we actually calculate the capacitance? So I'm going to erase this picture. This is just like a general capacitor. could have any shape. And there's three main types, like three basic shapes of capacitors. We have what's called a parallel plate capacitor, where you literally just have two plates next to each other. We have a spherical capacitor. So like here's one sphere, and then you surround that with another sphere on the outside. So hopefully you can see, like, it's hard to see just from a cross section that these are spheres, but yeah, like maybe you charge like this one Q and this one minus Q. So there's a potential difference between them. There'd be an electric field from that positive plate to the negative plate, and this would be a capacitor. And the other is going to look, here I'll write these down, parallel plate, spherical, and I'll say Q and minus Q. And then the cylindrical one looks very similar just in the cross section, where we have just like one cylinder inside another. So again, they look the same. It's the details, this one curves around, this one's just coming out of the board. So again, let's say we have Q and minus Q. And again, the electric fields for the last two cases are going to look the same, but just positive to negative. And so basically the idea is to find the capacitance of any particular system. And again, for these three, these are like the common shapes for capacitors, because these are ones where we can actually calculate the capacitance. However, we're only going to do that for this one case. The reason why is when you have I'll explain why we're not going to do that for the spherical and cylindrical one. But the basic idea is, remember that capacitance only depends on the capacitor itself. Basically it depends on geometry. Like here it can depend on the area of the plates and the separation between them. Here it would depend on like the radii of the spheres or the radii of the cylinders. Yeah, I guess it could also maybe depend on the length for the cylindrical one. But yeah, it doesn't depend on how much charge you put on it. So the approach is, say we place a charge, or we separate the charges. So we charge a capacitor to some value Q. That means one plate's positive, the other is negative Q. And theoretically, we could find the electric field. So yeah, we place a charge Q, find the electric field. We also want to find a relation between the electric field and the potential, which is basically given by this equation. Now, this is why we're going to restrict ourselves to the parallel plate capacitor. Because remember, actually I wrote this wrong, there's an approximately equal there. So again, this would be valid for, say, a very small delta x. But in general, that equation does not work. It only works if you restrict yourself to a very small delta x. And the smaller delta x, the better your result is. However, I mentioned when we talked about that equation that there's one case in which this is exactly correct. It's an exact equation, and that is if we have a constant electric field. And that's why we cannot look at the spherical or cylindrical case, because here we want to find the electric field, or the relation between the electric field and the potential. But the electric field depends on the distance from the center. So here we'd want to measure like the electric field as a function of the radius, but it varies as we go from one plate to the next. So we can't really use this equation. Now, we can make that equation exact by introducing that limit. You take the limit that delta x goes to 0, and in a calculus-based class, this is something you would do, because we'd have an equation we could work with in that case. Sorry, but here we can't really do. Same thing with the cylindrical one. So we're just going to look at a parallel plate capacitor. So there's kind of two steps. I'll just erase the whole thing. Get rid of everything. Okay, so we've got a parallel plate capacitor. So step one, we're going to put charge on it. So we have Q and minus Q. And that will create an electric field. Okay, now there is a little bit of a problem here, which I've drawn. When you get near the edges of the parallel plate capacitor, the electric field's lines start kind of curling, and that can be a bit of a problem. However, we're saying the plates have an area A, and the separation between them is D, and we're going to assume that D is very small. Like if you separated these plates, you'd have a significant curvature near the edges. But if D is small compared to like the dimensions of the other dimensions of the plate, then we can basically ignore what we call edge effects. So let's do that. We have these two plates very close together, which is typically what we would do. Okay, so step one, we're going to use Gauss's law. So let's draw a Gaussian surface. And we always want to remind ourselves that Gauss's law is tricky. It's kind of deceptively tricky. And the reason why is, in general, it's a fairly complicated thing. Like calculating the flux through a surface, there, just as a reminder of what Gauss's law is, the flux through any closed surface is equal to the charge enclosed divided by epsilon naught. And to actually calculate the flux, though, we have to have a completely enclosed surface and calculate the flux of the whole thing. Generally, that's very complicated. And so we don't really calculate the flux all that often. The only times we do it are when it reduces to something that's very simple. And this is one of those cases where the electric field exists between the plates, and that's basically it. There's no significant electric field outside. In the region where it curls out like this, that's small enough that we can ignore it. So in this case, we can say that the flux is the electric field times the area. Which is equal to Q over epsilon naught. So again, just a reminder, to use Gauss's law, we have to calculate the flux through, like say this is a rectangular box. It has to be an enclosed surface, so it has 6 sides. So we have to calculate the flux through each, like all the sides, and add them up. However, the electric field is only passing through one of these surfaces. And again, the curvature at the end, that introduces like that cosine theta term. But again, that's going to contribute such a small amount we could ignore it. And so again, the flux is the simple electric field times area. And again, that's extremely rare that that happens. When you consider all the cases Gauss's law could theoretically be used. But pretty much this is always the case in the times that we actually use it. But I will point out, say we only had one plate. Say we just had Q, and we drew a Gaussian surface around it. And in this case, the flux would be 2 EA. Because we'd have an electric field crossing through this surface, and an electric field crossing through that surface. And so again, it is a little bit, you do have to be very careful, in general, using Gauss's law. Okay. So that's kind of the first step. We have a relationship between the electric field and Q. What we really want is an electric field between Q and V. So now we need an electric field, or a relation between the electric field and the potential, and that's what we have here. For a parallel plate capacitor, we can say that the electric field would simply be V over d. The potential difference between the plates is V, and the distance is d, so that's it. And so now we just have to put these together, which is kind of straightforward. We have Q equals epsilon naught E times A. I'm going to write down epsilon naught while we're at it. Okay, so yeah, we've got a relation between Q and E, and now let's just plug in E is V over D. So yeah, E is it's V over D, and then times A. And we can rewrite this so just epsilon naught A over D by itself, and then times V. Now, if we compare this to the basic equation, Q equals C times V, we can see that the capacitance for a parallel plate capacitor is epsilon naught A over D. So again, it only depends on geometry. You have, bigger, it depends on the area of the plates and the separation between them. And that's it. It doesn't matter what the charge is, what the potential difference between them. So the capacitance is really just property of the capacitor itself. And yeah. Okay, so I'm going to write this down. And let's kind of build a capacitor. So we put two plates next to each other. Let's just kind of start over. So say we have two metal plates with a radii of 4 centimeters. And let's say the difference separating them is 2 millimeters. So we want to, so we've got these two plates. Now we want to calculate the capacitance of this system. All right, so we've got our formula. So we have epsilon naught, that's 8.85. I'm going to move this down a little bit. Just, I'm feeling I'm going to use the whole board going across. And it's times 10 to the minus 12, so I'm going to put that, it's 10 to the 12 on the bottom. Now the area is pi r squared. So r is 4 centimeters. So this would be, if we square this, we get 16 pi times centimeters squared. And then we divide by d, which is 2 millimeters. Okay, so simple enough. Problem is units. We have to get farads out of this whole mess. So, yeah, I'm going to erase this. Here, I'll draw it up here. Two parallel plates. Radius r, separation d. Okay, so the first thing we want to take care of, we've got centimeters and meters. Let's say 1 meter is 100 centimeters, and we square that. We can say there's 1,000 millimeters in a meter. So at least we've got rid of the like non-base units. Now there's one more conversion factor I'm going to write down over on the right. So remember this equation that relates the potential energy and the potential. So this is energy, that's measured in joules, charge is in coulombs, voltage is in volts, big surprise there. So a joule is equal to a coulomb volt. And joule is also, energy, think like work, which is force times distance. So we have a Newton times a meter is a coulomb times a volt. I'll just write that here. Okay, so let's, we're going to wind up using that. So let's say a coulomb times a volt is a Newton times a meter. Let's do that the other way. And we also have that coulomb is equal to a farad times a volt. Let's say a farad times a volt over a coulomb. So first off, let's check the units. Now again, I highly recommend doing problems like this, where you just write out all the units and the conversion factors. Again, it might look like a nightmare, but it's really not that hard. I mean, it's just 1 meter is 100 centimeters, right? We all know that. So, you can write it like this. 1,000 millimeters is a meter. And again, all these conversion factors are on the equation sheet, so you could always just look those up if you don't happen to memorize them, which is fine. You don't need to memorize them all. Okay, so it just takes a little practice, but if you get in the habit of this, it's extremely helpful. Okay, so let's just go across the top. We have coulomb squared times centimeters squared times meters squared times millimeters, Newton, meters, farads, and volts. And then let's go across the bottom. We have a Newton times a meter squared. So there's a Newton times a meter. Here's another one. Then we have millimeters, centimeters squared, meters, and then coulomb times a volt. And then finally at the end we have a coulomb, and we can see that everything here cancels out except for farads. Okay, but there's a little problem here. And then we don't really want to express this capacitance in farads. And the reason why is, let's just kind of look at the numbers. We get a reasonably large number on top, 8.85, 16 pi, that's going to be around like 50. So we're looking at maybe 450 times 1,000. So yeah, we're looking at the numerator numerically is around 450,000, very large number. But on the bottom, we have dividing by 10 to the 16th power. So this is 10 to the 4th, because remember it's 100 squared. That's 10 to the 4th times 10 to the 12. That's 10 to the 16th power. And so this is going to give us an incredibly tiny numerical value we measured in farads. Typically, we want to either go with nanofarads or even lower than that, like picofarads. So that prefix P is 10 to the minus 12. So I'm thinking we might, let's go with picofarads. So we can say 10 to the 12th picofarads is equal to 1 farad. So then these cancel out. So do the 10 to the 12th. So now we're going to get our answer in picofarads. So here, 16 pi, I forgot my phone, so I'm just going to say that's 50. 16 times 3 is 48, so that's very close to 50. Here, I'm going to say 8.85, let's say 8.9. and then times 10 to the third on top. Now on bottom, we just have 2 times 10 to the fourth. And that would give us our capacitance in picofarads. Okay, we can cancel this out. So 50 divided by 20 is 2.5. So let's see, 8.9, 2.5. So I made some approximations here. So let's say the capacitance is just 22 picofarads. Okay. And again, that's actually not a bad number. This is like, I should have brought it down here. I have like some, you can buy capacitors just for like, playing around with electrical circuits. They're very frequently used in electrical circuits. And yeah, I have some capacitors around this side. If I showed you, maybe I'll bring it out later, but they're tiny. Well, I mean, if I hold up like this, well, most of that's just the 2 leads. The capacitor itself is extremely tiny. And the reason why capacitors tend to be very small is because we put them in electrical devices. So what do they do in electrical devices? A lot of things. One of the main things, or one thing they could be used for is storing energy. Like if you charge up, if you have a capacitor, let's just say we have Q and negative Q. What happens if we put a wire, a conducting wire, between them? The charge is going to flow down this wire. We want the charge, positive charges attracted to negative charges. We can think of positive charges flowing until they're equalized and the charge is 0 on each. And again, so this charge is flowing down a wire. That's called a current, which is something we haven't discussed yet, but you've definitely heard the term current. You plug something in an outlet, you get a current. So we could actually have this, say, light a light bulb. It wouldn't light it for very long, though, because it's just going to be like a one-way flow of charge. It just goes from one plate to the other, and then it stops. But they can be made to store energy and then release it very quickly. I've actually got a picture I could show you. I should have just left this open before I started. Let's see if I can find this picture, though. It's kind of an interesting one. So here, this isn't it, but these are actual capacitors shown with like a pencil, just to give you an idea of the size. So again, we want to make them very small so they can fit in things. Oh yeah, so this is a really cool picture here. This is like a whole room just filled with capacitors. So what that is, I think it's powering a laser. Yeah, there's 10,000 capacitors. And it stores 60 megajoules, so that's 60 million joules of energy, and it can release it in 1 millisecond. Yeah, and it powers lasers. So you want to power a laser, like a very energetic laser, and just like where are you going to store all that energy to send to it? Well, here you go. 10,000 capacitors, and you can do that. So yeah, really interesting. It says here they're trying to produce sustained nuclear fusion. So that would be really great if they can pull that off. That's my old textbook. That's from like the 1970s or 80s or something. I don't know when it was originally written. So it's a little bit outdated when it comes to fusion research, but so that's one definite application of capacitors is storing energy. There's another, they can be used, there's like a time delay. Like say we put this is a chapter in the book, we skip it. Let's say we like we have a circuit with a battery and a resistor, which again we'll talk about those later, and a capacitor. But just think of a resistor. It's something designed to like impede the flow of current. And yeah, so you've got like a simple circuit, and if you flip a switch and like connect the battery to the circuit, the capacitor will like charge up kind of slowly. And then if you allow them to discharge, so if you like have the wire just going around or just directly across whatever, so charge can flow from one to the other. Again, it's if you have a resistor, if you have a significant amount of resistance impeding that flow of charge, it can be made to charge rapidly or slowly. And so you could even power a speaker with something like this, where you've got these magnetic speakers where basically you have this membrane that just oscillates back and forth. And I believe they are made by, like you can create a magnetic field with electricity. Something we'll talk about later. So like say you have this coil where you can energize it and say this is like a metal bar. If you suddenly turn this into a magnet, it's going to pull the bar over, and that can move the speaker. And then you can have it like spring loaded so it goes back. Yeah, I'm not sure exactly the details of how that speaker would work, but if you just energize that coil, that's just going to pull the speaker one way and just hold it there. So if you have it like pull the speaker and then disconnect it, then it's going to go back the other way, and then you pull it again. And if you keep doing that very rapidly, you can have the speaker oscillate, which would create a sound. And so again, capacitors play a role in that. One way you can do that by just like hooking up a speaker to a battery is you can wire it up in a way, which I won't go into the details here, we haven't even started electrical circuits, but basically you have your speaker connected to the capacitor, so like the voltage across them is the same, and nothing's going to happen until you achieve a certain voltage, and then the speaker is going to go, and then you can discharge it and it's going to go back, and then you recharge it and keep going backwards and forwards. And so yeah, the capacitor plays a very vital role in making that work because it charges up. You can control how quickly you want it to charge up or discharge. And yeah, you can design a speaker that's just going to keep oscillating back and forth at a particular frequency, which you determine by the value of the capacitor and also the resistor connected to it. So they can be made to store energy. Lots of circuits use capacitors. And something we're going to talk about a bit later, alternating current. Yeah, we've got a couple of, like an alternating current, that's when the current can be driven in both directions. Like sometimes it's forcing current one way, sometimes the other way. And capacitors play a very different role in circuits like that. They can be used as filters to prevent certain frequencies from getting through, or like only allowing certain frequencies to get through. And there's another device called an inductor that also works as a filter. And by combining them, you can, like one prevents high frequencies from going through, the other prevents low frequencies from going through. And it depends on like how you set up, like what the value of your capacitor or the value of your inductor is. But you can set it up so that there's like a narrow range of frequencies that can exist in that circuit. Because if they're too high or too low, they're either blocked by the capacitor or the inductor. And this is kind of how a radio works. So if you have at least an old-fashioned radio, where you have an antenna that's collecting radiation that's being broadcast by the station, your antenna is picking up all the frequencies that are being broadcast. But you can tune your radio and just listen to one frequency. Like if you listen, I don't even know what frequencies there are, but I think there's like 97.9. So you turn in, I think that's megahertz. It's yeah, that station is broadcasting at that frequency, and you can design your receiver to only allow that frequency to exist in your circuit. So it kills off all the other channels, and otherwise you just hear static. They'd all be overlapping. And it's kind of interesting. I mentioned before, capacitor is basically two conductors near each other. But I mentioned that really there's no limit, there's no reason it's limited to two conductors. If you have like a third conductor, that would affect the capacitance overall. And it turns out you are a conductor. And I don't know if you've ever seen one of these before, but like old radios, believe it or not, they actually existed before like remote control. So if you wanted to change the station on the radio, you went over and had to turn a dial. You couldn't just push buttons on the remote. And that could actually be a problem sometimes, because the way that, turning that dial, what that does is it affects the capacitance to like allow a particular frequency to get through. And the problem is that you're a conductor. So if you go over there and you adjust it and get the sounding just right, you tune into the right frequency, when you leave, that affects the capacitance, and so that can kind of change the frequency away from what you actually set it to. So, I kind of think we're getting a little off topic here, but ultimately the point is capacitors, we generally want them to be small enough to put in electrical devices. And here, 4 centimeters, that's a little less than 2 inches, but that's not something that's necessarily very small. And so, how can we actually build? Like I showed you that picture with capacitors, they're like the size of a pencil lead with those leads at the ends, but they're not that big. So, how do we do that? Well, we only considered one capacitor. It's called a parallel plate capacitor. There's different designs. Maybe you could build one that would, be a little more compact. Actually, I will talk about one way we can make a fairly compact capacitor. Basically, it's a parallel plate capacitor, but a way to make it compact. And but there's something else we can do to increase the capacitance, and that is put something in between the two plates, like an insulating material. You can't place a conductor between them. If you place a conductor, then the charge is just going to flow right through them. So in order to maintain the two, the positive and the negative charge, we need an insulating material between them. So again, I'm going to erase this problem. We see this as actually a reasonable value for a capacitor, even though it's a bit on the small end. A lot of commercial capacitors are in the nanofarad range, which are significantly bigger than this. So we built a fairly large capacitor, didn't get much out of it. But again, this could be a useful capacitor. But we want to make it smaller. And the question is, what happens if we put something in between the two plates? And again, we're talking about an insulating material. So here's our two plates. We have Q and minus Q. And let's put some material in between. And this insulating material is called a dielectric. Okay, so what does this do? And the answer, in a sense, is extremely complicated, because this object is made out of some molecule. It depends on what this object is, but in general, it's going to be made out of atoms or molecules. Let's start out with the simplest case. We'll start with something simple. Say we just have atoms. Like, say we have an atom, where we can consider it, say we have a positively charged nucleus, and we have an electron, spinning around. Now, the simplest picture that we could look at for an atom is we have this nucleus, which is positively charged, and the electron is just like a little ball of electricity, like the planetary model, like the sun and the earth. So they're just two distinct objects, and this electron is orbiting around. Okay. Now that's not the most accurate picture of what's happening here. But in this case, it's actually good enough, because the electron is orbiting very quickly. So in a sense, if you look at like the average over some time, there's no real charge separation. Like right now we have a positive charge here and a negative charge here, but a very short time later the negative charge is going to be here. If you look at like the average location of this electron, it's going to be right in the middle. And so we have this charged object where there's no charge separation. We can say the positive and negative charges just overlap. Now I want to compare this to something like the, say a water molecule, which is H2O. So say we have two hydrogen, and we have our oxygen here. And overall, a water molecule is electrically neutral. But let's, if you look at the details, the charge is separated. And again, I have to, I should probably look this up and double check. For some reason, this one always confuses me. Like, I think the negative charges are, like the oxygen is the more negative, negatively charged, and the hydrogen positive, but overall, this is neutral. So what this means is, let's see, oxygen, that has 8 electrons, each hydrogen has 1, so there's a total of 10 electrons that are kind of moving around this molecule. What it means is they spend more time near the oxygen than the other end, so this end is a little more charged. This is called a polar molecule. And actually, let's look at this case first. What happens if we apply an electric field? Our electric fields exert forces on charges. And the positive charge, the force on a positive charge is going to be in the same direction as the electric field. So the positive charges are going to be pushed to the right, the negative charges pushed to the left. So what this is going to do, it's going to rotate this molecule, and I'm going to represent it symbolically like this. Where the positive charge is over on this end, the negative charge is over here. I might think, well, that can't happen here, but you get the same kind of effect here. So this is like a polar molecule. This is just a symmetric atom. But you'll get a very similar effect. Because actually, there's another factor here that I didn't take into account. I just said the molecule is going to rotate. But it's actually going to do more than just rotate. It's going to stretch out a little bit. Because the hydrogen is being pushed this way, and the oxygen is being pulled the other way. So it's actually going to stretch out a little bit, which will further separate these charges. Now, if we apply an electric field in this case, again, we're going to get the same kind of charge separation. The nucleus is going to be pushed to the right, and the electrons are going to be pulled to the left, so they'll spend more time over on the left end. So in a sense, we get the same picture. Now, the results will be very different when you look at the magnitude. You get a much stronger effect here than you would here. But overall, you're going to get this kind of separation, charge separation. So again, this was neutral before, it's neutral after, but now they're shifted. And, same thing here. So it's still neutral, but the charges are separated. These are called dipoles, by the way. Kind of an idealized version of a dipole is you have, say, a positive charge and a negative charge. Well, literally just that. And they're separated by some distance d. So that's called a dipole. And again, that's why it's called a dielectric material. Now, water, for example, a water molecule has an intrinsic dipole moment because the charges are separated naturally. In this case, there was no charge separation, but when you put it in an electric field, it acquires a charge separation. So this is called an induced dipole. But so anyways, we have this dielectric material because in any case, we're going to get this result. So if we look at what's going on a molecular level, well, it's hard to draw it because there'd be so many molecules. But I'll kind of expand it. If you look at the electric field like this, if you look at the material inside, we've got all these dipoles that are going to rotate, so they're going to be like this. And so on, like all the way across the material. Now, if you look at just like some region inside, it's going to be electrically neutral. Like, going to just circle this region here. It contains a positive and negative charge. If I circle that, positive and negative charge. Typically, if you look at if you make your circle small enough, you can maybe just capture one charge. But if you look on any, finite scale that's not, that's bigger than just like a single electron or something, or the nucleus of an atom, yeah, we could draw a circle around a bunch of these interior things. And we're basically getting the same number of positive and negative charges. However, the ends, we're going to have these, like if you look at the end here, we're just going to have this buildup of negative charge on this end. And we'll have a buildup of positive charge on this end. So in the middle, it's basically electrically neutral, because everything is shifted a little bit, but it's not, we're basically, there's always a positive next to a negative. And so the overall effect, so again, what's actually going on inside this material is extremely complicated. You can have atoms being, like the orbit of the electrons as being, from going from like a circular orbit to an electrical orbit, like the shape of that electron cloud could be altered by the electric field. Molecules can kind of rotate. All sorts of things can happen inside. But for most, the materials we're going to consider, basically, we can say that the electric field inside is going to be reduced just by a constant factor, which we call kappa. So let's say E naught is the electric field in a vacuum. Then the electric field in the dielectric would be that what you get in a vacuum divided by, this is a Greek letter kappa, looks like a K. You've got a picture, this is in the notes, I'll hold that up real briefly, kind of showing what I was saying earlier, a little better than I drew it on the board. But yeah, like the electric field inside, it's like a lot of these field lines run into this wall of negative charges, and so they're killed off. So the electric field is weaker, and that means that kappa has to be greater than or equal to 1. Where kappa is equal to 1 in a vacuum, just by definition, for any other material, kappa is greater than 1. I've got a table, and again, this is that situation. Whenever you look up data in a table, typically, particularly if you're going to use those numbers, you want to know where they came from, because it could depend on a lot of factors. But yeah, like I'll mention one in particular. So I'll write down, again, this is in the notes, but I'll write down a few values for kappa. Oh, and kappa, again, that's a ratio of electric field strengths. So it's just a number. It has no units by itself. So by definition, a vacuum is 1, exactly. And then we have air, which is 1.00054. So again, basically, if you're working with 5 significant figures, you might want to take this into account. We're not going to ever do that in this class. We'll never be working with enough precision where we have to take into account the difference between air and a vacuum. So let's look at something that actually does have some significance. Teflon, that would be 2.1. And again, that's a very significant number there. It's like the electric field inside Teflon, or like between the plates of the capacitor, would only be half of what it would be otherwise. So that's paper is 3.3. That one could be significant as well, not just numerically, but we'll see where we can actually use paper in the construction of a capacitor. And I'll just do two more. Rubber is 5.4, and then water is 80.4. So that one is huge. Now, kind of mentioned why this dielectric constant is so high for water, and that's because water is a polar molecule. The charges are already separated, and so if you apply a field, they're just going to line up, and yeah, you get a huge effect with water. And you can actually build a capacitor using water as part of it. Oh yeah, so one thing I mentioned, like whenever you look at a table, you have to look at, kind of the asterisk, like where does this information come from? And that can be very significant if you look at, say, water, because just there's a problem definition. What is water? I mean, pure water is just H2O, just a bunch of H2O molecules. But you never really find that. If you just go to your sink and get a glass of water, it's not just pure H2O molecules. There's minerals that are dissolved in it. And so, yeah, I imagine that this dielectric constant could certainly depend on what type of water, particularly if it's salt water, lots of minerals. Yeah, so you get a huge effect with this. Now I mentioned that you can actually build a capacitor using water. Seems kind of strange because we're talking about like electrical components don't mix well with water. But actually one of the earliest capacitors was, I think it actually did use water, or at least it could have. Say you have a glass container and you fill it with water, and the outside of the glass you have, say, like metal. So this is metal surrounding this glass. So you have to have an insulating material like glass between them. But basically you have this situation. You have conducting, you have like water inside, then an insulating layer, and then a metal conductor. So you have a conductor, an insulator, and a conductor. This is a capacitor. And you could put water in there. You kind of have to make it a conductor because pure water does not conduct electricity. So again, this is called a Leyden jar. This is like, I think, the earliest capacitor that really qualifies as like an invention. I imagine at some point in history, somebody, without realizing they were building a capacitor, had like two sheets of metal with something in between them. But this was designed specifically, to function as a capacitor. Okay, so let's, so what effect does this have, this dielectric have? So again, we can quickly kind of go through how we found the capacitance. Okay, let's get rid of all this. Yeah, let's just draw a parallel plate capacitor. So there's an electric field going from, say, positive to negative. And what we found before, like say, let's call this E naught. Because there's nothing in between the two plates. So from Gauss's law, remember E times A was equal to Q over epsilon naught. So the electric field in between the plates, E naught, was Q over epsilon naught A. So now the electric field, let's look at our capacitor with this dielectric in between the two plates. Okay, so our electric field over here would be Q over kappa epsilon naught A. And similarly, the potential difference between the two plates is the electric field times the separation. And so let's put these together. So here we have Q would be kappa epsilon naught AE. So we have kappa epsilon naught A. We moved all that over. So that's Q. Sorry, I wrote this one down wrong. The potential is the electric. Let's write this equation down. Okay. So, yeah, now we plug this in. The electric field is V over D. So we have kappa epsilon naught A V over D, and I'm going to write it like this. So comparing with Q equals CV, we can see that the capacitance for a parallel plate capacitor would be kappa epsilon naught A over D. Where before we just had epsilon naught A over D. That's what we got for looking at a parallel plate capacitor in a vacuum. And we could put a K in there because K in this case is just 1. So I'm actually going to put the K over here because this is true in general. So yeah, the parallel plate capacitor more generally, if you have a dielectric material, basically you get the same result as before, but you multiply by the dielectric constant. And again, we saw that can be a significant factor. Some like materials you could easily use in electronics, not like water, but yeah, like the biggest solid here was rubber, which was 6.7. Yeah, that was fairly significant. Okay, so yeah, that's one way you could increase the capacitance. Because again, we had a fairly large capacitor, just barely measured something in like picofarads. Or maybe we want to get to nanofarads, so that's still a big factor. And so it's kind of a fun way you could build a more compact parallel plate capacitor. And you need conductors, of course, to build any capacitor. So one conductor you could use is simply aluminum foil. And what's nice about that is it's flexible. So imagine you have a sheet of aluminum foil, and then you put an insulator on top and another sheet of aluminum foil. So I mentioned like one of the dielectric constants is paper. You could simply use paper as your insulator or your dielectric. So you have like aluminum foil, and then paper, and then aluminum foil. And you can have like a long sheet of this. So you can make a fairly large area, reasonably high capacitance, but then you've got a capacitor that's really long. Well, then just roll it up. These are flexible materials. So you can literally just roll it up into a cylinder and, kind of fit a lot more in there. So, yeah, typically though, capacitors are measured in like nanofarads or picofarads. I saw in a catalog where they sell science supplies, there's a 1 farad capacitor that's not that large. I'm not sure quite how they did that. But yeah, that's kind of interesting. I'm trying to think of like what I could do with it, and then maybe I'll get one and see if I can do anything fun with it. But yeah, like I really want to look into like how they got a farad into something that you could easily hold in your hand. But yeah. Okay, so let's do one more thing before, there's one more thing we have to cover for capacitors, and that is one of their uses is to store energy. So let's say we have our parallel plate capacitor. And let's say I take a certain charge Q and move it from one plate to the other. Let's say I take this charge Q, and so this is going to acquire a negative charge, that's going to acquire a positive charge. And, just move this over. But, like initially, say it's neutral. So if I just remove one charge, these points are barely charged at all, and it's not that difficult to move the charge over from one plate to the other. Now, the way you'd normally charge a capacitor, you probably have a wire connecting these plates and you'd go that way around. Let's just look at moving it directly across. So initially, it's not that hard to do. However, now there's a little bit of charge. This plate became slightly negatively charged, this one is more positively charged. So now if you want to move this second charge over, well, remember the electric field now is pointing to the right. And it's not a very strong electric field because we only moved a small charge over. But now it's the force due to this electric field. Again, we're assuming this is a positive charge. Now we're going to be fighting this electric field to move this second charge over. And what that's going to do is it's going to make the charge on each plate bigger. So now the third charge is going to have to fight a bigger electric field. And you can see initially, if you want to charge a capacitor, it's very easy to do, to start moving charges over. But the more you move them over, the more difficult it becomes. And so the question is, if we charge up a capacitor from, like, say, 0 to some maximum voltage, how much energy is actually stored? Like, the energy that be stored is whatever you had to do to move these charges over from one plate to the other. That's how much energy is stored. And so what we're going to do to figure that out, it's kind of complicated because just moving one charge, like if you're, here, put this here, like if there's a potential difference between the plates V, if you want to take a small charge, like say you're just going to move a very tiny charge over, so that won't really have a big effect on the plates or the voltage between them. So moving a small charge, the energy that is required would just be Q times V. But again, we're starting with 0 and going up to some final voltage. So let's make a plot. So on one hand, we plot Q and we plot Q as a function of the voltage. And remember, Q is equal to CV. So like they're directly proportional to each other. So we start at 0 voltage where there's not going to be any charge because they start off neutral. So we start with no potential difference, charge is 0. The more we increase the charge, or the more we increase the voltage, the more charge is going to kind of build up on the plates. So graphically speaking, this is kind of backwards because we apply a voltage and that's what moves the charges over. But I guess we could look at it, that's how we do it in practice. But we could imagine just physically pushing charges over, so Q would be our independent variable. And the more charge we move over, the greater the potential difference between the plates. So if we want to find out how much work it takes, let's just move a small amount of charge. Say delta Q. The amount of work that it's going to take to move that small amount of charge will depend on the voltage it's at. And again, that's why we have to restrict this charge to be small. If we pick a bigger charge, the voltage is going to change significantly as well. But if we just make delta Q small, we can just say it's at a voltage V. So the work would be delta Q times V, which is basically the area of that rectangle there. If you make delta Q small, see, really, there'd be like this voltage would just have like a flat top. We have this little triangle on top as well, which we're ignoring. And that's because, if we can make delta Q smaller, then it's, those triangles will be insignificant. And again, this process can be made exact, but we can do this just fine in an algebra-based class because this is just a linear relation between the charge and the voltage. Okay, so we can represent the work done as equal to the area underneath this voltage curve. So if we go to some full Q, if we want to charge up to, here, let's draw it like this. So to go up to some particular, let's say Q max, that's what we're ultimately going to charge it to. Well, what is the voltage here? The voltage would be Q over C. So the voltage here would be Q max over C. Okay. So again, we're representing the work that we had to put in moving these charges around by the area. So in this case, let's get rid of this. We want the area of this entire triangle. So the total work required, the triangle is just 1/2 times the base, which is Q max, times the height, which is the voltage. So we could write it as the voltage, but let's just stick with what we have here. Q max over C. So basically the work that was required was Q max squared over 2C. And that's how much work we had to put into it, but all that energy that we put into it is stored in the electric fields between the plates of the capacitors, and that could be recovered. So in general, we say the energy stored in a capacitor is, let's get rid of the max label now. Because we have Q as our, axes label, so I wanted to go to a particular value, so I called it Q max. But in general, the energy stored in a capacitor, there's different forms. Remember, at some value Q, we're at some potential V. So we could just say simply 1/2 QV, where Q is a charge on the capacitor, V is the potential difference between the plates. And again, we can always combine that with Q equals CV. So that's what we did before. If we let V equals Q over C, we'd have Q squared over 2C. You could also, here, I'll write that as well. Or we could also write 1/2 CV squared. So we can write it in the basic equation just in terms of charge and potential. We can write it purely in terms of charge or in terms of voltage. So basically, I like just having, on the equation sheet, you have this and this. And again, just combining these, you can easily get these other two results. There's actually one more thing I want to mention here. I know this is going kind of long, but just because we're on this topic, so we've got our parallel plate capacitor. And we have this electric field between the plates. cross-section area, A, and separation of the plates, D. Let's ignore the dielectric constant, just say it's in a vacuum right now. Keep things simple. We can say the energy stored, and I'm actually going to write out the word energy. We can write that as 1/2, let's see. Yeah, we want to kind of write the electric field in terms of the energy, or the energy in terms of the electric field. So we have the capacitance. Let's write it this way. We can write it this way. 1/2 QV squared. That's, sorry, 1/2 CV squared. Sorry. Trying to just finish this one up. Okay, so the energy is 1/2 CV squared. So we got that 1/2 Q times V, where Q is CV, so we get 1/2 CV squared. And the voltage is the electric field times the distance. So let's kind of plug things in. We have 1/2. The capacitance is epsilon naught A over D. And the voltage is E times D, which is squared. So we wrote the energy in this form. And then we plugged in the value for the capacitance and for the electric field. So basically we have 1/2 epsilon naught A times D. Because here we have, oh sorry. I'm going to write this as, okay, 1/2 epsilon naught. We've got an electric field squared. We've got the area, and then we have D squared divided by D. So I wrote it in this particular form. Okay, now, why are we doing this? Well, look at where the electric field exists. It exists between these two plates of the capacitor. And so the volume that the electric field takes up would just be A times D. And so if we take the energy divided by the volume, we get 1/2 epsilon naught E squared. So this is an important result. One of the main reasons, this is called the energy density. This is like the energy divided by the volume. So for a given volume, we can see how much energy was in that volume. And we can see that the energy density is proportional to the electric field squared. And again, this is very useful. And we're not going to use this again towards the end of the class, but where we're going to use that, we're going to talk about electromagnetic waves, which contain electric fields and magnetic fields, and they carry energy. And so this idea that energy density is proportional to the electric field, that's going to come up later. So yeah, I think we'll stop here for now. So a long lecture, I'll just assign like one topic for the day for this one. So yeah, that'll be it for capacitors, at least for now.